So you see my screen, right?
Yeah, yeah, we see your screen. Do you want to take a, just go to your next slide to make sure that it's moving? Yeah, fine. All right, well, why don't we get started? So our speaker today is Camilla Scolini. I'm happy to introduce her as the Jack Eddy Fellow who's working with me here in the Space Science Center. Unfortunately, thanks to COVID, she wasn't able to actually move from Europe yet. So she's in Belgium, where she finished her PhD, but we're hoping that she's going to come to UNH by the spring. So she finished her PhD this year at the Catholic University in Leuven in Belgium, and then was awarded the prestigious Jack Eddy Fellowship by UCAR and the NASA Living with a Star program. Prior to that, she obtained her MSc and BSc in physics at the University of Trieste in Italy. She's a very highly motivated and productive young scientist. She already has 5 first author papers under her belt, and she just finished her PhD, so that's awesome. And, it's already been she started 3 weeks ago with me, and it's been a great pleasure to work with her already. So her work is on modeling CME evolution, and she'll be doing more of both modeling and in situ work, working here at UNH. And we'll hear about all of this now.
Thank you. Thank you. Can you hear me? Yeah?
Yeah.
Okay. So thank you all for joining. Good morning. It's already late afternoon for me. Yes, so in this presentation, I will present you the work I did during my PhD in Belgium at KU Leuven and the Royal Observatory of Belgium. And I will talk about the modeling of magnetized coronal mass ejection and the study of their evolution and space weather impact from the sun to 1 AU. So I will start with giving a bit of motivation. Then I will introduce you to the basics of the EUHFORIA model, which is the main modeling tool I used in my work so far. Then I will provide an overview of the various observational methods that you can use to reconstruct the CME parameters from observations at the sun. I will present you some applications and case studies I worked on and how I applied the aforementioned methods for my studies. And finally, I will conclude with providing a summary and an outlook for the future. I don't know if I shall expect questions in the meanwhile, but well, I don't know. You're welcome to ask any question whenever you want, as for me. Okay, so a bit of motivation. I think this slide well summarizes the starting point of this study. So if you look at the main drivers of intense geomagnetic storms, so at Earth, previous studies clearly highlighted that coronal mass ejections are the main drivers of intense space weather disturbances to the geomagnetic field. Composing almost 90%, triggering almost 90% of the main storms. And in particular, 2 populations of CMEs can be identified. The majority of the intense storms are driven by individual CMEs that propagate from the sun to us without interacting with any other CME structure. And those is what I call single CMEs, which compose of magnetic ejectas and CME-driven shocks and sheaths. But almost 30% of the intense geomagnetic storms are actually caused by multiple CMEs that interact among each other on their way to the Earth. And therefore, being able to understand and model and eventually predict the characteristics of these events at Earth before they actually arrive at our planet is critical for providing reliable predictions of the space weather environment before the situation actually happens. Okay. So the main modeling tool the main tool I use to study these events is the EUHFORIA model. EUHFORIA stands for European Heliospheric Forecasting Information Asset. And it's a space weather modeling and forecasting tool that's been developed at KU Leuven, where I did my PhD, and at the University of Helsinki by Jens Pommel and Stefan Putz. And actually, there is a long-term goal for making it the real backbone of a full sun-to-Earth space weather forecasting tool, which will in the future include not only CMEs, but also solar energetic particles and the actual signatures and effects on the ground, such as induced currents on the ground. So in my PhD project, I actually focused on a very specific part of this large-scale project, which is the exploration and assessment of the space weather predictive capabilities of CME models in EUHFORIA, in particular of some of the magnetized CME models that are currently available. I have a bunch of publications which I listed here, and so this was my main goal of my PhD, the main focus of my PhD project. Although I also took a detour and investigated quite a lot how to improve more simple CME models that are currently used for forecasting at centers worldwide. So if you want to know more about the so-called cone CME models, I will spend a few words on that later on as well. You can rather look at those publications. I will not cover those results in this presentation. So the main questions that were open when I started my PhD, EUHFORIA was a very young model, and so the CME modeling had not yet been extensively tested, and the predictive capabilities were not assessed yet. So the first question I try to answer is how well can EUHFORIA predict the properties of individual CMEs at Earth in terms of magnetic fields and ultimate impact on geospace based on observations at the sun. Secondly, I turn towards more complex scenarios, in particularly focusing on CMEs that interact with each other on their way to the Earth, and trying to answer the questions of how the properties of single CMEs can be altered by the interaction with other structures, and how the space weather impact of those CMEs is likely to change, and how well EUHFORIA performs in studying these events. So more complex and more realistic, perhaps, scenarios. So EUHFORIA, what is EUHFORIA? EUHFORIA is a model for the solar corona and for the inner heliosphere. It can be thought of made of two parts. There is a coronal model that employs a semi-empirical WSA, which stands for Wang-Shili-Argy model, as input to run to reconstruct the configuration of the corona. It requires an input magnetogram, so a 2D map of the photospheric magnetic field at the solar surface, and it then extrapolates the magnetic field configuration up to a few solar radii, assuming a potential field solar surface model. And from 2.6 solar radii on, it extrapolates the magnetic field, assuming it's more or less completely radial, up to 0.1 AU. And at 0.1 AU, this is the outer boundary of the corona in the model. And employing some empirical parameters, it basically converts the information of the magnetic topology at that height into 2D maps of the plasma parameters, such as the one for the radial speed, which I'm showing here. Those plasma parameter maps at 0.1 AU are then used as as inner boundary conditions for the heliospheric part of the model, which is a time-dependent radii ideal MHD model, solving the MHD equations in time and space for the full inner heliospheric domain up to 2 AU, although exceptions are the polar regions, which are not modeled. And here we see a movie showing a steady-state solar winds on the equatorial plane of the sun, with projections for the main spacecraft and planets. So this is the typical output I work with in EUHFORIA, and you're going to see those kind of movies more and more later on in the presentation. Okay, so these previous slides concern the way EUHFORIA is able to go from from magnetograms to the modeling of the steady state ambient solar winds in the inner heliosphere. And on top of that, you can model CMEs. So regardless of the specific model you use, CMEs are always inserted as time-dependent boundary conditions at 0.1 AU. So that's the height, that's the reference height where we will be interested in determining the CME parameters at. And currently we have several models for CMEs available. The first one that was implemented is a cone model. So this is the kind of model that's, as I mentioned previously, it's currently used for forecasting at NOAA and other forecasting centers. It treats CMEs as spherical objects of uniform speed and temperature and density, and it doesn't prescribe an internal magnetic field inside CMEs. So those are unmagnetized spheres that are inserted into the heliospheric domain and that are overlaid on top of the interplanetary magnetic field solution coming from the solar wind description. So the major, one big step that was that underwent EUHFORIA is the passage from a cone model to a first flux drop model, which in this case is a spheromac, linear force-free spheromac model that provides a first description of the internal magnetic field of CMEs, which are still modeled as spheres. But it's a first step towards more ambitious flux drop models, such as the toroidal model or the Gibson and Lowe model or even the Fry 3D model. So those will be the ultimate, I mean, they are considered kind of better representing the 3D global structure of interplanetary flux drops as we think of them, and they're currently under testing in EUHFORIA. But yeah, when I started my PhD a few years ago, I was particularly involved in the transition from the simple cone model approximation into the spheromac model. So that's what I'm going to focus on. The main parameters that are needed to simulate CMEs in EUHFORIA can be classified into main groups, which involve the description of the kinematics, of the geometry, of the magnetic properties of the CMEs, and of the thermodynamics. And it's extremely important in a forecasting approach to assess how well we can determine those from remote sensing observations of the sun in order to ensure predictions with sufficiently time. In my work, I started with some methods that were already available and tried to reconcile them into a global scheme that could be applied to CME events almost routinely in preparation for EUHFORIA runs. So the kinematic and geometric parameters of CMEs at the sun can be obtained from observations in the corona. And one of the methods that is most popular to do such kind of estimations is the graduated cylindrical shell, or GCS model, which can be applied simultaneously to observations carried out by multiple spacecraft at 1 AU. So we have typically a combination of SOHO observations and stereo observations of the same CME event. And by the fitting of the actual observations with CME structure that is a prescribed shape in 3D, which resembles a croissant. So you see the wireframe projected in the three different field of views of the three spacecraft simultaneously. You can adjust the orientation and details of the geometry of your CME wireframe until you're satisfied with how it reproduces the feature that you observe in the corona that you decide it's your CME of interest. So here I marked the leading edge that we were interested in fitting in this particular case in the three field of views, and how the GCS model wireframe was then used to match the observations and to then estimate the various properties regarding defining the geometry of the CME in terms of CME direction of propagation, and CME width. And the application of this kind of procedure to consecutive images can be then used to estimate the speed of propagation of your structure in the corona, including the contributions associated with the translational motion of the CME axis and the expansion speed of the cross-section of the CME over time. Yes, so such kind of methodology applies until the edge of your field of view, which typically allows you to go up to 15 solar radii in the reconstruction. But EUHFORIA, in EUHFORIA, the inner boundary of the heliospheric model, so where we insert the CME in our simulation is a 0.1 AU. So then assuming a simple self-similar evolution of the CME and the constant speed and no rotations or deflection of the structure, you can kind of extrapolate the parameters to 0.1 AU to get the initial parameters describing the kinematics and geometry of your CME for EUHFORIA simulations. Regarding the magnetic parameters, of course, again, the idea would be to estimate them as close as possible to the actual inner boundary of the model, so 0.1 AU. But magnetic fields in the corona are not, I mean, we cannot measure them. So you need to typically look closer to the sun in the low corona. And in particular, the parameters I was interested in to perform my simulations using the spheroMAC model were the flux drop chirality and orientation, for a start. The flux drop chirality of CMEs based on in situ observations have been found to be, in most of the cases, consistent with the chirality of the erupted flux drop estimated based on the chirality of the source region which originated the CME itself. So, and this kind of estimation can be carried out by looking at the presence of and the skewness of corona loops observable in UV images. So in this case, here you have a sigmoid, forward S sigmoid observed in EUV. And therefore, these kind of observations can make us estimate that the eruptive flux drop from this region will likely be a right-handed flux drop. Of course, notable exceptions are reported, and this should not be considered as a 100% correct approximation, but it's an approximation. So that's the starting point for such kind of studies. The second parameter that's important once you have once you assume you know the handedness of the eruptive flux drop is the orientation of the structure and of the magnetic axis of your eruptive flux drop. So that's is typically estimated based on the orientation of the underlying polarity inversion line, which is also, again, assumes that your eruptive flux drop doesn't undergo any rotation or deflection in the early propagation, and it can also be particularly difficult to estimate in case we have curved polarity inversion lines that lead to an eruption, because in this case it's difficult to assign a single orientation to your structure. But as you'll see later on, you can find different levels of complexity and observational observational complexity in different events. So I will show you some application of these approaches for ideal textbook cases, and then I will turn towards more complex cases where actually this was less straightforward to estimate. So in addition to the flux drop chirality and orientation, the third parameter that needs to be quantified to perform an observation-based simulation of a spheroMAC CME in EUHFORIA is the amount of magnetic flux. In particular, the toroidal magnetic flux is the flux you need to prescribe in your simulation. So that controls the amount of twist and amount of magnetic field and the magnetic field strength that is in your flux drop. So this could be estimated from the amount of reconnected flux, which is the amount of magnetic flux that undergoes reconnection during an eruption event. So this can be estimated from different observational proxies, and it can be computed once you know the area of the observational proxy marking the position and location of the coronal of the loops that underwent reconnection during an eruption by integrating over this area the magnetic fields from photospheric observations. So this approach requires you to basically do two things: assess the area of interest and overlap the area of interest on top of your photospheric magnetic field observations to compute an estimate of the reconnected flux. And different observational proxies have been identified in literature and proposed. In my work, I tested this kind of approach over different proxies, in particularly first focusing on post-eruptive arcades, which are bright coronal loops forming after the eruption of a flux rope, of a CME flux rope. Flare ribbon areas, which actually mark the foot points of, or are thought to mark the foot points of those bright loops down into the photosphere, and coronal dimmings, which provide an indication of the location of the foot points of the CME legs in the corona. As a first case study, I started with looking for a textbook case that could provide a baseline for the best case, best performance scenario obtainable. So I specifically looked for a single Earth-directed fast CME event observed by multiple spacecraft with an optimal separation in the ecliptic plane to perform a reconstruction of the CME initial parameters using the GCS model in the best way possible. So typically, large angular separations are the requirement here. And so here you have a view of the spacecraft, the position of the Stereo spacecraft with respect to Earth during this particular event I chose. The CME launched on the 12th of July of 2012. It's a very famous event, previously studied by multiple authors. And here you see a GCS reconstruction in the Stereo B and Stereo A field of views, and a view from Earth, lower down in the corona. Secondly, this CME was also optimal because it was erupted from a source region that was very close to the disk center, therefore limiting the projection effects, entering the calculation of the estimates of the reconnected flux associated to this eruption. It presented a clear UV sigmoid indicating a positive handedness, right-handed flux rope eruption. The polarity inversion line, contrary to the previous case that we showed I showed you a few slides ago, was characterized by an almost straight geometry. And the post-eruptive arcade was also very well delimited, very stable in time, and provided an estimate of the reconnected flux quite robust. And in situ, this CME was later seen as showing very clear, typical signatures. So an interplanetary shock preceding a turbulent sheath and followed by a magnetic ejecta. Again, the flux rope type, in terms of chirality and orientation, well matched the estimated parameters of the sun, indicating little rotation, little deflection. And it was also characterized by a strongly southward magnetic field. And therefore, it triggered a strong geomagnetic storm, which was also an important requirement for the kind of study that I was doing, because the main goal was that of assessing how better EUHFORIA using a spheromag model predicts the impact of such structures on geospace compared to the traditional oversimplified cone model. So by reconstructing the CME initial parameters using the methodology I just explained, I performed two starting simulations with EUHFORIA, one with the cone model and one with the spheromac model. And one of the strengths of the cone model is that it actually has been proven to predict quite well the arrival time of CME structures at Earth, which is of course an important aspect of predictions, together with the magnetic field predictions, which because magnetic fields are the main the parameters that's controlling the impact on and the interaction with the planetary magnetic fields. So in this case, the first exploratory simulations highlighted that spheromac CMEs propagates much faster than the cone counterpart if initialized with the same speed. And that's by investigating the model outputs could be related to the presence of a strong Lorentz force acting at the CME solar wind boundary and outwardly directed, so indicating an expansion of the CME structure as a consequence of the internal high magnetic fields present in these kind of models and inducing an expansion that was not present in the cone simulations, and which led the front of the CME to propagate faster than the cone counterpart. So the first result that we were able to present was that as a mitigation strategy, initializing spheromac CMEs using a reduced speed to balance the extra expansion works well for several cases, and this reduced speed can not necessarily be prescribed ad hoc, but can be estimated based on estimates of the expansion and propagation speed of the CME in the corona using the GCS reconstruction. So also in an observation-based approach. So once we were able to reproduce the propagation of the leading edge in our simulations, we turned out to the improvement in the magnetic fields estimate at Earth. And in this slide, I'm going to show you two movies. On the left, you're going to see the north-south component of the magnetic field in the cone CME simulation on the ecliptic plane. And in the next movie, you're going to see on the right the same quantity, so the north-south magnetic field, in case of a spheromac, using a spheromac model. So yeah, so here what you see is a very weak magnetic field all the way from the sun to the Earth. Of course, this is not scaled with the radial distance, so it's getting weaker as the CME propagates, but it's weaker all the time, all the way. The spheromac simulation, on the other hand, looked as something much more obvious. So here we have the magnetic ejecta propagating and going through Earth. In terms of in situ predictions, yes, the goal was to quantify really how much are we improving by using this kind of more sophisticated model in terms of predictions of the magnetic field at Earth, and possibly also going all the way down to the surface, estimating the expected strength of the geomagnetic storms. So I used here an empirical relation, solar wind, DST coupling function based on O'Brien and McFerran, just to give you an idea about how much we are gaining there as well. So it turned out that for cone CME simulations, as expected, the magnetic field is very weak because there is no treatment of the internal magnetic field associated with the CME. And therefore, also the north-south component is basically flat, and the DST index prediction is all the way close to zero. On the other hand, running the spheromac simulation, we estimated that the peak magnetic field and peak north-south BZ improved by a significant number of percentage points compared to the cone simulation, so up to 70% percentage points for BZ, for B total, and up to almost 80 percentage points in BZ, not necessarily exactly at the Earth location, which is the dark red curve here, but looking at spacecraft located at slight separations with respect to Earth, the prediction was even better. So this gave us a baseline of how well euphoria with the spheromac can perform compared to the cone model, and how much we are gaining, despite the fact that we are spending much more time in trying to reconstruct the magnetic parameters of the CMEs for our simulations. But yeah, this was a very, a very unusual case because it's considered to be a textbook case in the stereo area. And so later on, in the second part of my PhD, I turned towards a more complex situation, which is also one of the most important ones for the space weather impact, which is the situation in which two CMEs interact in interplanetary space. As CME-CM interactions have been proven to amplify the space weather potential of individual CME structures. So the question I asked myself is also, how does this amplification evolve in space and time as the CMEs propagate from the sun to the Earth, so as a function of the interaction phase? And also, if there is a range of heliocentric distances in the heliosphere where interacting CMEs are more likely to trigger strong space weather disturbances as a consequence of their interaction. And normally we're used to think about space weather impact at Earth of CMEs, and therefore we call it, or it has been called, geoeffectiveness. However, since now I'm kind of looking at the space weather potential all the way from the sun to the Earth, I'm gonna talk about helioeffectiveness as the potential impact, the potential space weather impact at a generic distance from the sun of the CMEs involved in terms of strength of the total magnetic field and of the strength of the north-south component of the magnetic field. So as a case study, in this case, I selected a sequence of 3 CMEs that were observed in September 2017. So there was an unusually active region originating all of them. The first 2 were in very rapid succession, only a few hours of difference in launch time, and they interacted, as you can see here, as seen in LASCO images, interacted immediately while in the corona. The first CME was the slowest one, and the second one was about 500 kilometers per second faster than this one. So the interaction occurred already before the height corresponding to the inner boundary of the euphoria model, or approximately at that height. And then a few days later, a third CME was launched from the same active region, and it was again faster than the previous 2. Therefore, while propagating into interplanetary space, caught up with the previous structures and triggered a major geomagnetic storm at Earth. This geomagnetic storm was so strong, most likely because of the interaction among the structures. So looking at the in situ signatures, at Earth, spacecraft observed the passage of a first magnetic ejecta, which I marked in orange, and it corresponds to the structure, the merged structure of CME1 and CME2. And this first ejecta had a forward shock propagating through it that could be associated with the third ejecta, which came later on, a few hours later, and it showed a very relatively complex structure, and with different periods resembling magnetic ejecta, and some periods in between that were more turbulent. Previous studies assessed that this propagating shock driven by the third ejecta and propagating into the previous 2 structures likely increased the geoeffectiveness, so the impact of the structure at Earth, by a factor of 2 in terms of the minimum DST. So our questions were, how well can euphoria reproduce these estimates, and how these estimates at Earth descends from an amplification of the space weather potential all the way from the sun to the Earth. In this case, I expanded the methodology to estimate the reconnected flux, not only to the post-eruptive arcade, as I did in the previous study, but also considering flare ribbons and coronal dimmings. Here I'm just showing you for the first CME how the areas covered by the various proxies differ and how they map to very different regions in the photosphere. So it's not surprising that considering the 3 signatures, I obtained very different estimations for the reconnected flux, up to covering 1 order of magnitude, although the uncertainties are estimated to be around 50% of the estimated values. So in this sense, we can consider the different proxies to provide a consistent estimate, and this estimate should be considered not as an exact value, but rather as an order of magnitude. I also tested these estimates against statistical relations, which are very forecasting friendly, because they just need as input the flare information on the flare peak intensity measured by GOES to then to estimate the reconnected flux during eruption. And the 2 methods were quite consistent, so suggesting a potential way for forecasters to kind of estimate this parameter just based on easy to use statistical relations. In EUHFORIA, I performed the simulations of the 3 CMEs, which, as you see here, propagates from sun to the Earth and impact directly the Earth. In terms of geoeffectiveness amplification at Earth, to compute that, I ran simulations by adding progressively the CMEs one after the other. So in a first simulation, there was only the first CME. In the second one, there were the combined CME1 and CME2. And in the last one, I had all the 3 CMEs to estimate the effect of CME3 on enhancing the magnetic field in the preceding structures. And this estimated an increase in the geoeffectiveness of a factor 2.5, consistent with measure valued at wind and consistent with previous estimates based on in situ observations. And going to the minimum DST predicted, the estimated amplification of the minimum DST was about a factor of 1.8. So we were able to confirm the estimates based on previous estimates performed based on observations and theoretical arguments, but we also managed to investigate the full evolution of the interaction from the sun to the Earth, thanks to the modeling outputs that cover the full 3D space. So we looked at how the various interaction phases relate to the amplification of the magnetic fields inside the preceding ejecta carried out by the compression induced by the following CME. So here I have 3 snapshots where you see the meridional plane, the Earth is kind of here. Yeah, and the third CME is erupted after the combination of CME1 and CME2 propagates, and in time it catches up and interacts in different phases. Later on, we focused on the Sun-Earth line, and we computed the ratio between the maximum magnetic field and the maximum absolute value of BZ between runs with and without CME3. So an amplification factor of 1 means that there was no amplification inside the preceding ejecta compared to the case when the following ejecta was there, while an amplification factor higher than 1 means that the first ejecta was compressed and enhanced in the space weather potential by the action of the following ejecta. So we found, first of all, a very close relationship between the phase of interaction, so the pre-interaction phase, the phase where the following shock interacts with the preceding ejecta, and then the phase when the shock enters the preceding sheath into a more mature phase, and the amplification factor. So this this also gave us indication that by the time the structures impacted the Earth, they were in the most appropriate configuration to trigger an intense geomagnetic storm corresponding to the peak phase here. So this is something that could not have been estimated based on only in situ data, and it made us wonder whether such peaks exist in all kinds of CME interactions, and therefore whether some distances from the sun are the ones that are more likely to be impacted by strong space weather conditions as a consequence of the interaction between different CMEs. So this is something that It seems to me it may be the case, but further studies will have to be carried out, more specifically focusing on this kind of question. Yes, so as a summary, during my PhD, I had time and pleasure to work with a combination of observational and modeling tools, in particular on the development of a robust observational method to reconstruct the CME initial parameters and optimizing them for euphoria simulations in order to optimize the space weather forecasting of CME events at Earth. Of course, only a few tests on case studies was carried out so far, but we are actually going on with testing on a larger set of events. The SpheroMac model proved to be a significant improvement compared to the traditional cone model, but it still presents a lot of limitations that I haven't focused on here that will hopefully be mitigated by the implementation of more sophisticated flux models in the future. Efforts are already ongoing. And as I mentioned, further investigation on the role of CME interactions in space and time as space weather drivers is something that had to be investigated more, but yes, so far this is first evidence that this might be the case. And I'm at the end of the presentation. I just wanted to give an outlook on my UNH study. As Reka said, I'm going to work on a combination of in situ observations and modeling to investigate the evolution of CME structures and how their complexity changes as the structures propagate and interact with different solar wind structures. So I hope I'm not over time. And yeah, I thank you very much for your attention. And I will be happy to answer any question you have.
Thanks for the nice talk, Camilla. Do we have any questions?
Maybe I can stop sharing.
Oh, well, you may want to share just in case
Okay.
people have questions specifically to the
yes.
slides. I do have a question right off the start. So you mentioned the September 2017 CMEs and their interaction. So I know that these have also been modeled through NLL. And I think it was Christina Lee who ran a bunch of those models and has a paper out on that. Have you compared the results from the NLL model to the EUHFORIA model for this? How does it compare?
So if I'm not mistaken, I think the paper you're thinking of was specifically focused on the September events at Mars. Could that be?
Well, I know that they modeled it all the way out to Mars, but
yes.
did not have any outputs at Earth.
Yeah, so I think the paper you're thinking of, so it was treating these events, but actually, so I showed you 3 CMEs. After those 3, there were 3 others that were erupted while the active region was closer to the limb and eventually were observed at Mars. Yeah, so I think the major point is that Enlil doesn't only has the cone model available, and so it doesn't account for a treatment of a description of the magnetic field inside CMEs. So if it's the paper again I have in mind, I think they focus more on the arrival time at Mars and on the information they could recover on the dynamic. I mean, a comparison for the dynamic pressure of the structure, but nothing on. I mean, they couldn't really
get a magnetic field.
Yes. Yeah.
Okay, and it hasn't been modeled with anything else, like in terms of the magnetic field structure, like the 3D core model by Christian Russell.
Oh,
I don't know if it has been. I'm just curious.
I honestly don't know, but a few days ago I searched for his papers on ADS and I didn't find anything. Okay. So I don't know if that's the right answer, but that's just what I know. If you know more, or if somebody else knows more, yeah, not as far as I know.
Okay. Great, thank you. Anybody else for questions? I think the easiest way is if you just raise your hand in Zoom and then we can get to you, or if you want to type any questions into the chat, that works too.
Hey Camilla, that's Noe.
Hi.
So at the beginning, you mentioned kind of the, the flux rope and the SPHEROMAC CMEs, and kind of the flux rope being some of the.
Should I go back? Oh.
What are your, I mean, at the end of the day, we know that CMEs are probably not SPHEROMAC, but at the same time, it does work decently well.
Yeah.
For like, what are you, I mean, what are your thoughts generally on that? Like, something that we know is definitely not really the morphology of CMEs actually does, as you just showed, does a pretty good job at forecasting or reproducing the actual morphology.
Yeah, I didn't really focus on that, but yeah, I think the point is that the SPHEROMAC model indeed doesn't reproduce the global structure of interplanetary flux ropes. So what I learned from applying this kind of model to various events is that it works well if, as far as you are trying to model the front and the central portion of a full flux rope. So like here, this portion, but it performs poorly as far as you start moving towards the flanks. So in that sense, I would say one of the major limitations of the SPHEROMAC model is that it's kind of can be expected to work decently well for central encounters and CMEs directed towards us or to any other spacecraft, but its performance decays with the impact angle with respect to the CME center.
Yeah.
So that's the, yes, I think that's the main.
I mean, also, I'm just thinking loudly kind of, but I know you spend quite a bit of time trying to, we didn't talk about that, but the initiation of this SPHEROMAC at the 0.1 AU boundary and how to incorporate the expansion. And
yeah.
Do you think this will, how do you think this will be affected by different magnetic field morphology? Like, do you think it would be just a directly transposition of, if you start with a flux rope, or it will actually have to redo a full study of how to initiate this?
Honestly, I don't think. So the main character, so the main responsible for this expansion was the magnetic. In the SPHEROMAC case, was a magnetic pressure gradient developing at the boundary with the solar winds. So in this sense, I mean, I think in case of another flux rope model, I don't expect this to be significantly different, but I'm not sure about magnetic tension. So I haven't yet tried, but I will.
No, I guess. I mean, that's very.
Yes.
Okay. Thanks.
Anybody else for questions? I have one more if nobody else wants to go. So this, I'm not sure if you can give me a good answer or evaluate this. I'm just curious, you know, given your extensive experience with EUHFORIA, do you have an idea of how this compares to, say, the SWMF model or any other sort of competing models out today?
Well, yes, okay.
Field, so unlike
yeah, so with Enlil, we had quite a lot of exchange over the years, and it seems one of the main differences is in how well the ambient solar winds is reproduced over the long term. Statistically speaking, for a random day, how EUHFORIA and how Enlil perform. Enlil is a much more mature and older model, so the people working on Enlil have had decades to optimize the parameters leading to the modeling of the solar winds and entering the coronal part of the equation. So I have to say, people are working on that in EUHFORIA, and it's still an ongoing thing. For for
so based on that, would you trust the NLL results more if you were just, say, trying to model the solar wind and not a CME magnetic field structure?
If I have to say, no, there's no, yeah, I will say it here. Yes, but simply because of the more, yes, I think just because of, like, you know, in terms of time spent on working on that, the NLL is a bit more, yes, more
advanced.
More advanced, yes. Okay. Yes, but I hope
then it's lacking the magnetic field in a CME, so that yes, already takes it out
exactly.
From that running.
Yes.
Okay.
Yes.
And then what about the SWMF from Michigan, like that code?
I never tried comparison of any kind. Yes, just one note is that here we are still limited to a semi-empirical coronal model. So any model that would employ a more realistic description of the corona, I would expect, for example, the predictive science model. It's I mean, much more sophisticated and realistic in the coronal area. So EUHFORIA was born as a forecasting model. So it's also one of the main points is that it is running quite fast and can give you a solution and a prediction in less than an hour. So this is one of the strengths that we are working to keep and to when developing a more sophisticated treatment of the various environments entering. Yes.
Yeah, that makes a big difference than not having to wait weeks for results.
Yeah.
You're trying to forecast something.
I guess it's just a different perspective, and yeah.
All right, great. Thank you. Okay, well, are there any other questions? Okay, if not, then let's thank our speaker. I think we can do an applause if reactions. There we go.
Virtual applause is also.
Virtual applause.
Yes, that's great. Okay, thank you very much for joining. It was a pity that I couldn't do it in person, but yeah, I hope maybe next time, next seminar I can give it in person, I hope.
Exactly. All right, well, thanks everybody. Thanks for joining, and yeah, thanks Camilla.
Thank you.
Have a good day.
Thanks.
Bye.